Welcome to Kiosk.
Thank you for the introduction, and also thank for the organizer for offering me an opportunity to give a talk at my home institute, Kiosk. So today I'm going to talk slightly different topic from what has been talked throughout the conference. I'm going to mainly talk about my major interest, something called differential graded manifold, in short, DG manifold, and want to show some construction that I made through the geometric concept coming from the exponential map. So the talk will consist of those four stories. I'm going to start with the classical ones in the ordinary geometry, exponential map, and how we think of the exponential map as a formal map using the infinite jet. And then we talk about graded manifold and how to extend those notions to graded manifold. And next concept will be the Atiyah class, which is related to the extension of this graded manifold into differential graded manifold. I'll pose a question, and then the answer is related to this Atiyah class. And then finally, we go to the exponential map on differential graded manifold. And in the final result, I'm going to show that the construction we make induces something called L-infinity algebra, which Kapranov introduced when he was studying the Rojansky-Witten invariant. And then the construction I make is a generalization of that in a sense that the one that I construct for a special case of the differential graded manifold induces is quasi-isomorphic to the L-infinity algebra originally constructed from the Kapranov. Okay, so the exponential map, it appears in Lie theory and differential geometry. So starting with the Lie theory, so we start with a finite dimensional Lie group, and then we have a tangent space at the origin of this Lie group. So we have a corresponding Lie algebra. And then we know that there is a well-known map, exponential map, and this exponential map is locally a diffeomorphism near origins. So if you want to get this local diffeomorphism in a way that we want to record this local diffeomorphism by looking at the infinite jets of this around this origin, we get this induced morphism on distribution at the origins, 0 from the Lie algebra and identity from Lie group. And they are isomorphism because this is a local diffeomorphism. And then it turns out that it's also very well known that the distribution at 0 is the symmetric algebra of G. This construction is, I guess everyone knows what it is. And the distribution at the identity of the Lie group is known to be the universally enveloping algebra of G, which appeared in the previous talks when he was talking about the Hopf algebras. So UG is constructed as a tensor algebra of G quotient by this relation. And moreover, both SG and UG have coalgebras. Well, it was mentioned already in the previous talk, as I mentioned. It's a Hopf algebra. Both of them are Hopf algebras, in fact. But the structure that I'll be using is the coalgebra. And for those who are not familiar with the coalgebra, coalgebra is basically just the dual notion of algebra that you change the arrows of the structures opposite. So multiplication is A tensor A to A, but if you are looking at the coalgebra, you change the direction of the arrow, so you get a map from C to C tensor C for a coalgebra C. So SG and UG both have coalgebra structures, Of course, they have algebra structures, but we are not going to talk much about those algebra structures. Anyway, so the induced map was an isomorphism, and this isomorphism, in fact, is an isomorphism of coalgebras, so they preserve coalgebra structures, and we are going to call this PBW, which stands for Poincaré Birkhoff Witt map. This map turns out to be just a symmetrization map. One remark I may make is that this map does not preserve the algebra structure, associative algebra structure. Of course, this is commutative. This is non-commutative, so they cannot be isomorphic as an algebra, associative algebra. Hey, this is about the PBW isomorphism, which can be thought of as the infinite jet of the exponential map in Lie theory. And then we can do the same thing for differential geometry. So we start with a smooth manifold, and we choose an affine connection on it. And the exponential map is defined using the geodesic coming from the connection. So if you have a base point and a tangent vector, then this Tm goes to m cross m, where the first component is the starting point and the final point, the second coordinate is the destination. And then this is a bundle map where the projection to Tm to m is the vector bundle map, and m cross m goes to the first projection is the structure of this bundle. So using geodesy, we can define exponential map. And then again, we are going to look at the space of distributions. And then what we are going to do is actually, we're going to look at the distribution in the fiber direction at the origin. So at each fiber, you have an origin, and then you look at the distribution. So at each point of each fiber of Tm and m cross m, we are going to look at the distribution, and then what we'll get in the end as a bundle, looking at the all points from the base manifold, is the section of symmetric tensor of tangent bundle, STM. And Dm, also you can think of it as the universal enveloping of a tangent bundle as something called Lie algebroid, or this is just the differential operators on M. And so each of them corresponds to the distribution of Tm and m cross m, and there is an isomorphism because the exponential map is a local diffeomorphism along the zero section of Tm. So we again get an isomorphism, and of course this preserves the bundle structures. It also preserves the C infinity M module structure, and we again are going to call this Poincaré Birkhoff Witt isomorphism, or PBW isomorphism. What is D of M is the space of differential operators on M. Right, so as you may expect, both of them, section of SD and M, differential operators on M, they both have coalgebra structures over this ring. And this co-multiplication are given by deconcatenation. So you detach x1 times to xn by, at some point by reordering process. So sum of all those things, sum of all detaching n product is given by the co-multiplication. And using this co-multiplication, it can be easily shown that this Poincaré Birkhoff Witt map is an isomorphism of coalgebra and also is an isomorphism of C infinity M module. So it's an isomorphism of coalgebra over C infinity M. Again, this PW in this sense also do not preserve the multiplication which already exists naturally for STM and DM. So it's not an associative algebra map, but it's a coalgebra map. Sorry? So this is an isomorphism, but it's an R-module isomorphism. And then, in fact, they have a coalgebra structure, and it also preserves the coalgebra structure. Yes. Okay, so this map, as I mentioned, should be the infinite jet. That's the title. So I would like to explain that. So if you pick a point M from the base manifold and look at the fiber of Tm at M, you use the exponential map and compose with a function. And you have a map from a vector space to R, and you look at the Taylor series of this map. And then the Taylor series of this basically exponential map gives you the PBW map. So this really is the infinite jet. So PBW can be thought of as the fiber-wise infinite jet of this exponential map. So that's why we call it formal exponential map. Yes. Well, there is for DM there are two different explanation. One is the for DM. So let's say X and Y are differential operators. They are not vector fields, but it could be a composition of vector fields. And then, so yes, so I only need one. So if I have this, then it should be in DM tensor DM. So global explanation may be, which is easier to look at, is that if I have F and G, that's just the X applied to F times G. And then this relation agrees with the deconcatenation in a way that maybe I put arrow like this, and then if X is X1 composed with X2, let's say, then delta of X becomes the identity on F tensor with X bar on G plus X applied to F tensor with identity, and then you also have a X1 tensor X2. So X1 applied to F, X2 applied to G, and then you again have X2 tensor X1. So X2 applied to F and X1 applied to G, and sum of all this become the co-multiplication on differential operator. All right, so, okay. So we look at this geometric interpretation of the construction, let's say geometric construction of Poincaré Birkhoff Witt map, but then this can be completely characterized in terms of algebra. No need to have any geometry involved. That the Laurent Jengu, Stinon and Xu, they showed in 14 that this PBW map is completely determined by this recursive formula that this x n plus 1 is the n plus 1 tensor of the same vector x. So functions are preserved, vector fields are preserved, and higher symmetric tensors of vector fields are given by this formula involving only n tensors, although the input is the n plus 1 tensor. So by increasing the number of tensors, we get the complete characterization of this Poincaré Birkhoff Witt map. Okay. So for example, we started with the Lie algebra case, and then this picture agrees with the Lie algebra case in a sense that if we start with a Lie group, and then instead of looking at any vector field but left invariant vector field, because the vector in the Lie algebra is corresponding to the left invariant vector field on the Lie group, and then we choose the connection which is which is trivial, associated with trivial with respect to the left invariant vector fields, and then this PBW map turns out to be exactly just the symmetrization map. So this is the Poincaré Birkhoff Witt map from the differential geometry. A few remarks are in order that this inverse map is considered as a map sending differential operator to something called complete symbol. And this algebraic characterization of PBW, there was no need to think about the points, the points on the manifold or geodesics. We only need the connection and those formula, and we can completely characterize this PBW. And so we can think of this PBW as the formally defined exponential. All right. So we want to generalize this notion to something called graded manifold. To do so, we need to introduce what graded manifold is. As I'm starting to define graded manifold, I'm going to also define what differential graded manifold in next page. This definition is not considered as the proper definition, but for the purpose of this talk, the way I define is good enough. And most of the people who are working on this graded manifold, they mainly look at, well, let's put it this way. I haven't seen anyone thinking of the graded manifold in C-infinity sense. That is not an example of this type. So I think this is good enough. So I give you a naive definition, which is a lot easier to understand. So for those who are not familiar with this graded spaces, so Z-graded vector space is just a vector space if you don't think about the grading. But this vector space has a decomposition into direct sum of infinite vector spaces again. And each vector space, let's say Vk, is considered as all vectors in Vk are degree k. And so it's a finite sum of degree, let's say A1, K1, K2, K3 is a general element of the vector space, this graded vector space V. And then once we have this graded vector space, we can also talk about graded vector bundle over a smooth manifold. What it is again just a vector bundle, ordinary vector bundle. But then if we think of the grading as we did with the vector space, so if you look at the fiber, it's actually has a Z grading structure. So if you decompose like this for vector bundle, then this E is decomposed into direct sum of En, where the sections on En are considered as degree n. Okay, and then that's it. Z-graded manifold with space manifold M is just this Z-graded vector bundle. So there's nothing much interesting going on with the graded manifold itself. The interesting part is when you think of differential graded manifold, that this differential graded manifold, DG manifold, is a graded manifold equipped with a vector field Q. Q is the usual notion. So vector field on this graded manifold is defined as an element of derivation, space of derivation on smooth functions. And this homological, the adjective homological means that this C infinity M, the M itself has degrees, so smooth function have degree. And so Q increases Q is a map from C infinity Cayley M to C infinity Cayley M. And in terms of degree, Q increases the degree by 1. And the graded commutator is the Lie bracket here. And because the Q has degree 1, Q bracket of Q with itself is the twice of Q squared. And then we want this to be 0. That's what it means by homological. So in a sense, that smooth function with Q becomes a differential graded algebra is equivalent definition of the DG manifold for a graded manifold. Right, so there are several examples. One example is a Lie algebra. So starting from a Lie algebra, the G shifted by 1 is, by G shifted by 1, we mean a graded vector space whose graded vector space whose elements in G shifted by 1 is all in degree -1. This is just a notation. And we want the vector field on G shifted by 1 to be the Chevalley-Allenberg differential in a way that smooth functions are wedge of G dual. And then this Q is Chevalley-Allenberg differential on this space, so that the C infinity G1 with Q becomes the cochain, the standard cochain complex for Lie algebra cohomology. Another example is the smooth manifold. And then we are going to look at the tangent bundle. Again, we are going to shift the bundle, the degree of the bundle by 1, so that the fiber of this bundle has degree -1. And then we are looking at the drum differential as this Q, so that the smooth function becomes the space of differential forms. And then drum differential on them becomes a differential graded algebra, so that this becomes a DG manifold. So we have a complex manifold X. And then we're going to look at the anti-holomorphic tangent bundle of X, and then shift the fiber of this by 1, so that the fiber of this T01 shifted by 1 has degree -1. And then the homological vector field is going to be the Dobo operator. And then what we have is the smooth function is the space of anti-holomorphic forms. And then the Q is the Dobo operator, so that the whole thing is the Dobo complex. And this is a DG algebra. So the manifold is the differential graded manifold. One last example I want to introduce is, well, if you look at all of those, everything is shifted by 1, so that I thought I should introduce at least one thing that is in negative shifting. So if you have a vector bundle and you choose one smooth section of this bundle, and then E shifted by -1 with interior product with S, this section S, is a DG manifold also. It's also called the derived intersection of S and the 0 section. And so smooth function on this of this graded manifold is the wedge of E dual, so antisymmetric tensor of dual of E. But the degree convention is the opposite, that if you have a E dual element, and then that's in degree -1, and if you put 2 on there, then it's in the degree -2, and so on. So decreasing the number of tensor becomes a degree 1 map, so that interior product with S becomes a degree 1 map. And if you wedge S with S itself, that's 0. So if you do the interior product twice, then this becomes 0. And so this becomes a differential graded manifold. A particular example that people might be interested in is that when E is the cotangent bundle and S is the D of a function, then this people call it derived critical locus, which is a particular example of this framework. Okay, so what we were doing is I introduced the formal exponential map on the smooth manifold. And then what I want to do is generalize it to graded manifold. So I need to use the connection on graded manifold. And the connection on graded manifold is just the same way, except that we are in the graded setting that we have every time this F or X or Y, if the order of these symbols change, we get a sign like this, which we call it cosine sign. So the way the connection is defined is exactly the same as the usual classical case. The only difference is the sign, and then we require the connection to be degree 0. And also, torsion-free connection for torsion-free affine connection is when if you nabla xy minus nabla yx equals to bracket of x and y, and then because x and y has been changed, so we just put cosine sign inside there. So that's the torsion-free affine connection. So once we choose an affine connection, we do exactly the same with the classical differential geometry sense, that we can define something called Poincaré Birkhoff Witt map from the section of STM, where this M now is a Cayley M, so that this is a graded manifold, and also to the differential operators on the graded manifold M. And this algebraic formula, I just wrote it once again here, that these functions are preserved, vector fields are just as it is. And then if you have a n+1 symmetric tensor of vector fields, then it only involves the n tensor, and this also is n tensor, so we have a recursive formula which characterizes this PBW map. The nice thing that I mentioned is that we didn't need to use any points on the manifold or geodesics or something coming from the geometry. Everything defined algebraically. So even though we don't know much about the space of the graded manifold, we can do exactly the same for graded manifold. And then moreover, this section of STM and differential operators on M, they have exactly the same coalgebra structure except the signs. And then you again get an isomorphism of graded coalgebra as a result. This is something done by Liao and Stinan in 2015. Okay, so the question is, the whole thing that we did here, it does not involve any homological vector field. It only cares about the graded manifold, which I defined as a graded vector bundle. And what happens if I have homological vector field, so that some information on Q is on the both sides, and the TBW map preserve that structure coming from the homological vector field is the question. So I want to answer this question, and the necessary concept was something called Atiyah class. Okay, so Atiyah class originally was defined by Atiyah for holomorphic vector bundle over a complex manifold. So if you have a complex manifold, and holomorphic vector bundle over X. Then Atiyah gave several equivalent way of defining the Atiyah class, but one way we want to adopt is by looking at the smooth connection of type 1, 0, so that section of E goes to the holomorphic cotangent bundle tensor E. So this satisfies the nabla 1, 0. Nabla 1, 0 satisfy this condition that this partial is the holomorphic one. And so we're going to look at some operator which is commuting with the Dobo operator and this connection. So we have basically two form, but we are only looking at the 1-1 part of the two form. The complex two form decomposes into 2-0, 1-1, and 0-2 in the sense of the first one is the holomorphic part and the second one is the anti-holomorphic part. And then we are going to look at the 1-1 part of this. And so this R is an element of omega 1-1 of with coefficient in endomorphism of E. And turns out the Dobo operator applied to this R is 0, so this is 1 cocycle. And its cohomology class using the Dobo operator on E and X give you a cohomology, and its cohomology class becomes the Atiyah class. And the meaning of this Atiyah class is then it's an obstruction to the existence of holomorphic connection on E. Although you have a holomorphic vector bundle, you don't always have a holomorphic connection. It exists only when Atiyah class is 0. So using this technique, yes. It ends up it ends up independent of choice of connection. So that's governed by the cohomology class. So cocycle is chosen using the connection, but then cohomology class does not depend. Yes, thank you for the nice comment. Delta 1, 0 is global connection, but it's a smooth connection. No. It's not guaranteed that it exists. Okay, so we are using the same technique for differential graded manifold. So we choose connection. Well, for the convenience, I put the torsion-free connection. And then we are going to choose a section of the symmetric input is symmetric 2 tensor of Tm, and the output is the tangent bundle of M. So in a sense, this is S2 of T dual M tensor with Tm. It's a section of that defined by this formula. And this formula, in a sense, is just the Lie derivative of nabla along the homological vector field Q. But remember that this nabla is not in this space. It's not C infinity M linear, because the second function f satisfies the Leibniz rule, not linearity condition. So that's what happens. And turns out this LQ square is 0. And this Atiyah cocycle, as you can see, this is defined as LQ of nabla. So LQ of this Atiyah cocycle is 0. So it really is a cocycle. And its cohomology class in general is not 0, because nabla, although AT nabla is LQ of nabla, but nabla is not inside here. So its not in the coboundary all the time. So you get a cohomology class non-trivial in general. And then it turns out this is independent of choice of connection. So we can define Atiyah class like this. So this AT nabla I defined is called the Atiyah cocycle. And the Atiyah class of this DG manifold is the cohomology class. And the meaning is that it's an obstruction to the existence of a connection on the graded manifold, which is compatible with Q. So it also is related to the existence of a connection, certain connection. Okay, for example, if we start with a finite dimensional Lie algebra, then I mentioned there is a DG manifold associated to it. And then this is the space where the Atiyah class of DG manifold lives. Turns out there is an isomorphism to the, is it 1-2 tensor or 2-1 tensor? This is always confusing, but it's inside here. And then this Atiyah class is exactly under this isomorphism corresponds to the Lie bracket of G. So in a sense, if the Atiyah class vanishes, then this Lie algebra has to be the abelian Lie algebra. It's kind of interesting when I first saw this, that is from just the Lie algebra. You think of a differential gradient manifold, and something called Atiyah class governs the structure of the whole Lie algebra. Okay, second example, I'm going to look at the complex manifold. So from complex manifold, we have a corresponding differential gradient manifold. And there is a quasi-isomorphism from the space of vector field with the omegas, the anti-holomorphic forms with coefficient in holomorphic tangent bundle, with the Dobo operator coming from the holomorphic structure of holomorphic tangent bundle of X. And then left side is the Lie derivative with respect to Q. And so using this quasi-isomorphism, I said this is a good quasi-isomorphism because this quasi-isomorphism is closed under tensor, which means if I tensor the same thing twice, and if I tensor this thing twice, you still get a quasi-isomorphism. Even you take the dual, you still get a quasi-isomorphism. And so you get an isomorphism on the cohomology on both sides. Left-hand side is the space where the Atiyah class of this DG manifold lives. On the right side, this one is where the Atiyah class, the original Atiyah class of the holomorphic tangent bundle T10 lives. And then it turns out under this map, the Atiyah class of DG manifold coming from complex manifold corresponds to the classical Atiyah class of X. That's probably why we can call this Atiyah class. Another thing is the opposite direction, that if we have a vector bundle and choose a section, then I mentioned that I have a differential gradient manifold called the derived intersection of S and the zero section. Rather than giving you the complete description of this Atiyah class, I mentioned something that I recently computed, that if you compute the Atiyah class and find out when it vanishes, is exactly when the section of S and the zero section are clean intersection. And for those who are not familiar with clean intersection, then this is the definition, that in general, if you have a two submanifolds, their intersection may not be smooth manifold again, but if it's a clean intersection, this is again a manifold, and even more, the tangent space satisfies this relation. It's slight generalization of transversal intersection, and this, yes, so it's a slight generalization of the transversal intersection. Yes. What is? No, this X, Y, W are ordinary smooth manifolds. Of course, there is a notion of submanifold in the graded manifold, but for this, so intersection of S means the image of S is the M inside the E, and the image of zero section is the canonical way of getting M on the zero section of E, and those two, so those two intersect cleanly is the criterion. There. I have E to M, and then I have two maps going up. One is S, one is zero section. That if you have E like this, M, then this is the zero section. And you may have something like this as a S. And then I want these two does not necessarily intersect cleanly, but if intersect cleanly, then the Atiyah class coming from this information is zero. That's the claim. Okay. So these are about the Atiyah class. And then we go back to our business of talking about the formal exponential map. So we go to the formal exponential map for now differential graded manifold. So if I start with a differential graded manifold, we had a section of STM and differential operators on Colli M. And then this homological vector field Q give you a Lie derivative on Tm, which extends by the Leibniz rule to STM. And also you get another Lie derivative with respect to Q. It's an extension of Lie derivative with respect to Q to dm, which turns out to be just the graded commutator with Q. So apply Q at the end minus apply Q first and apply the remaining stuff. So we have two canonical differentials on these two spaces. And then the refined version of the question I had is that equipped with these Lie derivatives, does PBW preserve the differential graded coalgebra structure? So it was an isomorphism of graded coalgebra. What about the differential? And then if this is an isomorphism, then we can really call it a formal exponential map of the differential graded manifold rather than graded manifold. And the answer is one of my results with my two advisors, Dinan and Shu, that Atiyah class, it vanishes, is exactly the same thing as this PBW preserve the Lie derivatives. So I should have Lie derivatives here, Lie derivatives here. So it's an isomorphism of differential graded coalgebra. So the requirement for the isomorphism of graded coalgebra over C infinity M becomes a differential graded coalgebra. Isomorphism of differential graded coalgebra is when Atiyah class of this manifold is zero. Yes? It's really the isomorphism. Because if you don't look at the differential, it's an isomorphism of graded coalgebra. And the claim here is it even intertwines with the differential. So it's in honest sense isomorphism, not the quasi. Of course, if it's an honest isomorphism, then it's a quasi isomorphism, but it's more stronger than that. Okay, so this is one of the answer to original question. And then there are things that we can look at more. That, okay, this is not always an isomorphism of differential graded coalgebra. So how much it fails if Atiyah class does not vanish? Of course, it will be governed by the Atiyah class, but how much it fails? So we just look at the Lie derivative put back to the domain and subtract with the Lie derivative on the domain. And then we get a sequence of map where the first two R0 and R1 are just 0. The second map is the Atiyah cocycle. And yes, Q is a vector field. So Q is in vector field. And so if I have a vector in here, then LQ X is just the Lie bracket with Q. And then if I have a X1 to Xn, which is in the symmetric tensor of Tm, then LQ of X1 to Xn is the extension of this using the derivation law. So LQ of Xi and sum over I with X1 with Xi omitted Xn, but maybe I should use this straight L. That's the notation I use. This is the Lie derivative on the left-hand side. Right-hand side, if you have a differential operators on M, so maybe it's better I use, maybe I use D. And then the LQ, the Pauli LQ of D becomes the QD minus DQ with the signs involved inside here. So this, if you restrict again to the vector field, this really matches with this. So it's a two different generalization because there are two different spaces. It's just a generalization on each space of the Lie derivative on the tangent line. Okay, so we look at this failure, and then we realize that these RK, R2, R3, R4, well, R2 is the Atiyah cocycle, and the higher ones are completely determined by its curvature and their exterior covariant derivatives. And if curvature vanishes, then we have a nice formula like this. That's something we figured out. And then why do we care about this RK? Why do we care about this failure? It's because using these RKs, we can get something called L infinity algebra on the space of vector fields. Well, actually, yes, L infinity 1 algebra. This is just a convention using the degree. So we get a L infinity algebra on the space of vector fields. And so for RKs are given by this formula where each RK is in K tensor, input is K tensor and output is one tensor of Tn. Okay, so for those who first see this L infinity algebra, I briefly go through this L infinity algebra like this, that if you have a graded vector space, then L infinity algebra is just a graded vector space equipped with a sequence of maps that each Qi have I inputs of V and output is V, and it satisfies the anti-symmetric relation. And each of them has degree 2 minus I, and it satisfies something called generalized Jacobi identity. Generalized Jacobi identity, that in a sense that this is a generalization of Lie algebra up to homotopy. That if I write down first few axioms using Q1, Q2, Q3 denoted as the D and this bracket and tri bracket, then D squared is 0 is one of the conditions. And then D is the derivation on this Lie bracket is the second condition. And the third condition is the Jacobiator n this Jacobiator is 0 up to homotopy is what we have. And then there are infinite sequence of the relation involving Q4, Q5, Q6, and so on. And this is just a notational problem that here I use V and L infinity algebra, and these degrees are 2 minus I, but then we just shift the V by 1, then all Qi's ends up being just degree 1. So you have infinite sequence of map Ri, which corresponds to Qi, merging from the degree shifting. It all has degree 1. So that's why I use the notion L infinity 1 algebra, so that it's easier to write. Okay, so from this picture that we get an L infinity algebra, we apply it to finite dimensional Lie algebra. Then space of vector field is the wedge G tensor G. This is, in a sense, the space of the cochain complex of Lie algebra cohomology with coefficient in G with the adjoint action. And then LQ is the canonical Chevalley-Eilenberg differential coming from the adjoint action. And the Atiyah class, as I mentioned, is just the Lie bracket. Then turns out R3, R4, they all vanish. So if you take the cohomology on this, the Lie algebra cohomology with coefficient in G, then using this R2, you have a Lie algebra. That's one thing that I can mention. Another thing is something that I want to conclude with, that in '99, Karpanov introduced the L infinity algebra coming from the Keller manifold. He was studying the Rojansky-Witten invariant. And then he introduced L infinity algebra in the following way, that if you have a Dobot complex with coefficient in holomorphic tangent bundle, and you get an L infinity algebra on this, where the differential is just the Dobot operator.